Suppose A is a complex matrix, then we define a conjugate transpose of A as the conjugate of A transposed. So the order doesn't matter, well, we can take the transpose of A first, and then take the conjugate of the transpose. And therefore, if A had all real entries, then the conjugate of A would be equal to A, and therefore the transpose of the conjugate would be equal to the transpose of A. So for example, to find the conjugate transpose of A, we find the conjugate first. So the conjugate of a complex number with only a real component is equal to the real component, and the conjugate of 2 minus I is 2 plus I, and of I gives minus I, and then we have 0, 5 minus 2I, and minus 3I. And then to find the conjugate transpose, we just take the transpose of this matrix. So we have minus 2, 2 plus I, and minus I, and 0, 5 minus 2I, and minus 3I. And now we'll look at some properties of the conjugate transpose. So if we have a complex scalar S, and A and B are complex matrices, then taking the conjugate transpose of A, and then the conjugate transpose of the resulting matrix gives A. And adding two matrices and taking the conjugate transpose of the result is the same as adding the conjugate transpose of both matrices. And the same thing applies if we subtract those matrices instead. And multiplying a complex scalar by a matrix and taking the conjugate transpose is equal to the complex conjugate of the scalar by the conjugate transpose of the matrix. And the conjugate transpose of the product of two matrices is equal to the conjugate transpose of the second matrix by the conjugate transpose of the first matrix. So if A and B both had real entries, then the conjugate transpose is replaced with the transpose. And the complex Euclidean inner product can be expressed as a conjugate transpose of the vector B multiplied by the vector A. So this was similar to how we expressed the inner product between two tuples with real components, where the conjugate transpose of B was equal to the transpose of B. A square matrix A with R rows and R columns is Hermitian if the conjugate transpose of A is equal to A. And Hermitian matrices have real numbers on a diagonal, and their entries in their corresponding symmetric positions up the diagonal are complex conjugates of each other. And the eigenvalues of a Hermitian matrix are all real, and the eigenvectors from different eigenspaces are orthogonal to each other. So as an exercise, I'll let you verify this first property by finding the conjugate transpose of this matrix. And to find the eigenvalues of a complex matrix, we solve the characteristic equation. So what we get is 2 minus lambda by 1 minus lambda minus 1 minus I by 1 plus I, which is 1 minus I squared. And that's equal to 0. So therefore lambda squared minus 2 lambda minus lambda plus 2, and I squared is minus 1, so this expression evaluates to 2. So we have 2 minus 2. So if you factorize this expression, you get lambda 1 is equal to 0, or lambda 2 is equal to 3. And now to find the eigenvectors corresponding to lambda 1 equals 0, we have the product of the matrix A minus lambda I, so that would be 2 minus 0 is 2, and 1 minus 0 is 1. And we have the following entries off the diagonal, and that's multiplied by v1, v2 is equal to 0. So if you subtract 1 plus I on 2, multiply by row 1 from row 2, and do the algebra, you'll get zeros in row 2, and therefore you have the equation 2 by v1 plus 1 minus I by v2 is equal to 0. And if you set v2 to be a parameter t, then we can write the general solution, which represents all eigenvectors in the eigenspace corresponding to lambda 1 equals 0. So we'd have t, and when v2 is equal to 1, v1 is equal to minus 1 minus I on 2, which is I minus 1 on 2. And if you did the same thing for lambda 2, we'd have the eigenspace represented by the following general solution. So you'd have t by a basis vector with components 1 minus I and 1. And now to verify that both eigenspaces are orthogonal, we just take the complex Euclidean inner product of the two basis vectors. So we have I minus 1 on 2 by the complex conjugate of 1 minus I plus the second component by the complex conjugate of 1. So what we get is I plus I squared minus 1 minus I on 2 plus 1. And the i's cancel, and I squared is minus 1, so we get minus 2 on 2, which is minus 1, plus 1 is 0. So all eigenvectors between those two eigenspaces are orthogonal. A square complex matrix with R rows and columns is unitary if the inverse of the matrix A is equal to its conjugate transpose. But typically, we don't need to compute the inverse, and instead verify that the column vectors of A form an orthonormal set in the complex inner product space of R tuples with respect to the complex Euclidean inner product. And the same applies to the row vectors. And some other properties of unitary matrices is that the norm of the product of A with the vector V is equal to the norm of V for all vectors V in CR. And also the complex Euclidean inner product of a vector A by V with a vector A by W is equal to V dot W for all pairs of vectors VW in CR. So let's verify that this is a unitary matrix. So first we'll verify that the column vectors form an orthonormal set in CR. And you can do the same for the row vectors. So if we take the norm of C1, that's equal to the square root of the modulus of the first component squared plus the modulus of the second component squared. So that's equal to the square root of 1/2 squared plus 1/2 squared. And you'll get the same result for the second term. So here we'd get 4 1/4, or the square root of 1, which gives 1. And in a similar way, you can verify that the column vector C2 is also a unit vector, which I'll leave for you as an exercise. And now we'll verify that the complex Euclidean inner product between C1 and C2 is 0. So multiplying the first component of C1 by the complex conjugate of the first component of C2, and then plus a second component of C1 by the complex conjugate of the second component, which is 1 plus I on 2. So that gives minus 1 minus I minus I minus I squared on 2 plus 1 plus 2I plus I squared on 2. So minus I squared is minus minus 1. So therefore we have minus 1 plus 1 is 0. And I squared is minus 1. So we get 1 minus 1 is 0. And therefore minus 2I on 2 is minus I. And 2I on 2 is I. So minus I plus I is 0. So the column vectors are orthonormal. And therefore A is a unitary matrix. So as an exercise, try to calculate the inverse of the matrix and verify that it's equal to its conjugate transpose. A square R by R complex matrix is unitarily diagonalizable if there's a unitary matrix P such that the conjugate transpose of P multiplied by A multiplied by P results in a diagonal matrix. So in this case, P unitarily diagonalizes A. Now in particular, every square Hermitian matrix is unitarily diagonalizable, similar to every square symmetric real matrix being orthogonally diagonalizable. So this is because every Hermitian matrix has an orthonormal set of R eigenvectors, and therefore the unitary matrix P that unitarily diagonalizes a Hermitian matrix A has the orthonormal set of eigenvectors of A as column vectors. So note that there are other matrices other than Hermitian matrices that can be unitarily diagonalized, and these are called normal matrices, which have the property of the conjugate transpose by the matrix being equal to A by the conjugate transpose. And now we'll develop a process for unitarily diagonalizing a Hermitian matrix using an example. To unitarily diagonalize a Hermitian matrix, we follow the following steps. So first we find a basis for each eigenspace of the given Hermitian matrix. So to do that, we solve the characteristic equation to find the eigenvalues, and then for each separate eigenvalue, we solve the following equation to find the eigenvectors. So here, we found this basis vector for the eigenspace corresponding to lambda 1, and this basis vector for the second eigenspace corresponding to the second eigenvalue. And then we apply the Gram-Schmidt process to each of these bases to obtain an orthonormal basis for each separate eigenspace. So remember that for Hermitian matrices, all eigenvalues are real, and the eigenvectors from each separate eigenspace are orthogonal. So in this case, all we need to do to obtain an orthonormal basis for each separate eigenspace is to normalize each basis vector, because there's only one per eigenspace. So taking the norm of the first basis vector, we get the square root of the squared modulus of each component. Or we can take the square root of the inner product of the vector with itself. So we have minus 1 plus I on 2 by the complex conjugate of minus 1 plus I on 2 and plus 1 by the complex conjugate of 1. And that's equal to the square root of 1 plus I minus I squared on 4 plus 1. So that gives 2 on 4 plus 4 on 4, which is root 6 on 4, or root 6 on 2. And then we can find the norm of B2 by taking the square root of the complex Euclidean inner product of B2 with itself. So we have 1 minus I by the complex conjugate plus 1 by 1. So that gives 1 minus I squared, which is 2, plus 1 is 3. And therefore, to obtain a unit basis vectors, so we have B hat 1, we divide each component of the basis vector by the norm of the basis vector. So what we get is minus 1 plus I on 2 on root 6 on 2, which is minus 1 plus I on root 6. And 1 on root 6 on 2 is 2 on root 6. And B2 hat is obtained in a similar way. So 1 minus I on the norm and 1 on the norm. And in the final step, we form the unitary matrix P with its column vectors from the orthonormal basis vectors obtained from the previous step. So in this case, P has the first normalized basis vector in the first column, and the other unit basis vector in the second column. And using our matrix, being a Hermitian matrix, you can take the conjugate transpose of P, multiply it by A, and multiply it by P, and verify that the diagonal matrix you get has the eigenvalues of A on the diagonal, which we obtained previously. And I'll leave this part for you as an exercise. A skew-symmetric matrix with real entries is defined such that the transpose of A is the same as negating A. So as we can see, if we take the transpose of A, the zeros on the main diagonal don't get altered, and minus 1 gets swapped with 1. And negating A, we end up with zeros on a diagonal, and minus 1 and 1. So therefore we must have zeros on a diagonal for this to be true. Now the complex analog is a skew-hermitian matrix where the conjugate transpose is the same as negating A. So remember, to obtain a conjugate transpose, we first take the conjugate of A, which gives minus 2I, 1 plus I, minus 1 plus I, and 0. And then take the transpose to get this matrix. So we end up with minus 2I, and 1 plus I, and minus 1 plus I, and 0. And if we instead negated A, we get minus 2i, minus 1 plus I, 1 plus I, and 0, which gives the same result. So therefore, for a skew-hermitian matrix, the entries on the main diagonal must be either pure imaginary numbers or 0. And the eigenvalues of a skew-hermitian matrix are either 0 or pure imaginary.